This is a video for AQA Discrete Mathematics, Graphs and Networks, section 4.4, where we're looking at network flows and flow augmentation. So a reminder about what we've already met with network flows. The network has a source at S, where all of the arrows are coming away from S, all the arcs, and what's called a sink at T, where the arcs are all flowing into T. At every vertex, we'll see that the flow in is going to be equal to the flow out. On this diagram, of course, these are capacities, so that what we have at A is the potential of 10, 6 and 5 flowing into A, but only the capacity to take 12 away. We've met the idea of the max flow Mincut theorem. So for example, we could look at a cut, a simple cut which goes in that fashion there, which divides SDACB as one set and the other set as T, and we can see that the capacity of that would be 15 plus 7 is 22. There is a cut like this one here, and you can see that the value of this cut is the 12 plus 4, but not the 5, because that one is flowing out of the sink set into the source set. So we don't include the 5 to give us a value of 16, and that happens to be the minimum cut for this particular network. So what we want to be able to do is see if we can find an actual flow which has got a value of 16, and then we can quote the max flow Mincut theorem to say that must be our maximum flow. It's not possible in general to check every single possible flow, because there's just be too many of them, and the networks can be quite complex. So we have to have some algorithm which will allow us to work out a maximum. The way we do it is to start off with what's called a feasible flow, so an initial flow through the network of some value. As long as it works, it doesn't really matter, but one way of doing it is to choose an initial flow where there's nothing flowing through the network at all, so zero flow. And then we use what are called flow augmenting paths. So we find ways of improving, augmenting the flow within the network from our initial starting point. And the way we do this is, for example, if we say there's no flow initially, we then look at every single arc and decide, well, how could we possibly improve that particular arc? What changes could we make to the current flow? So we're going to first of all just consider from D to C. And if we think about D to C, if there's no flow in there currently, then we could possibly increase it by 4, because that would take it up to its full capacity. But in terms of decreasing the flow in that particular part of the network, we wouldn't be able to do anything. So we're going to create a new picture which has got 2 arrows on every single arc. One showing the increase, and a second one pointing backwards showing the possible decrease. Now we have to do that for every arc on the network. If we're starting off with 0, let's just do a couple more examples. So we could see that for S to D, we would have a possible increase of 8 and decreasing by 0. So all of the backward facing arrows, if we call them that, are all going to be 0, and all the forward facing ones are going to be the capacity of those particular arcs to start with. So we end up with this diagram. What I suggest you do is just pause the video and then make sure that you understand where all of those numbers have come from. We're now going to look for what are called flow augmenting paths. So a flow augmenting path starts at S and finishes at T and has these forward facing red arrows, all positive numbers. So for example, if we go across the top from S to D to C to T, so S, D to C to T, you can see that we've got 8, 4 and 7. Now those are the possible increases. So if we were to go along that path S, D, C, T, the smallest of those is 4. So we can increase or augment the flow along that particular route by 4. Having decided that we can make that change by 4, we now look at each of the numbers that we've got on the arcs and change them by 4. Now, so that the possible increase is now going to go down to 4 and the possible decrease up to 4 on this one here. So you can see that these are still indicating the changes. Because the capacity was 8, we could change in the direction from S to D by another 4 if we were able to. But if we look at S from D to C, we've actually got 4 flowing now, so the possible increase has now dropped to 0 and the possible decrease is now 4. So you can see the changes are all going to be by 4. The forward facing arrow is going to go down by 4 and the backward facing arrow up by 4. Now look at the route which is S, D, A, B, T. If you follow that route through, from S to D to A to B to T, you'll see that all of those forward-facing numbers are positive, 4, 6, 12 and 15. The smallest is the 4 at that part there, from S to D. So we can make a change there of plus 4. We'll do that change. So the forward-facing arrows are going to go down to 0. The backward-facing ones go up to 8. That indicates that we've got a flow now of 8 in SD. And in fact, that is what we now call saturated, because this has become 0. Changing all of those from D to A, that will become 2, and this one 4. This will drop down to 8, and go up to 4, and the 15 come down to 11, and the 0 to 4. So remember that we are going to decrease all the forward-facing arrows, increase the backward ones. There's one more flow augmenting path that we can consider, this time going from S to A to B to T. So if we look at that one, SA is 10, AB 8, and BT is 11. So total there, or the smallest number, is the 8. So we can change that to 0 and put a flow of 8 along that route. So add 8. So this becomes 8. The forward-facing one is going to be reduced by 8, and the backward-facing one go up by 8. So you can now see that we've got another saturated arc here. And now if we look at the pattern that we've got, well, there's no possibility of increasing from S to D, and we could go from S to A with 2, but then we reach a block where we can't go from A to C, so it's 0. We can't go from A to B, that's 0. We could go from A to D, but when we reach D, we've got a saturated arc here. So everywhere is now blocked. So we should have reached our maximum flow. What is the flow? Well, it's these backward facing numbers here, the 4 and the 12. We've got a flow here of 16. So let's have a look at that actual flow on a separate diagram. Remember, it's the backward facing arrow, so 8, 8. Here we've got 4, etc. So let's look at the flow pattern that we've got now. So there's our flow pattern, and we say, well, what is the maximum flow? And of course it's 16. We can see that there's 4 and 12 flowing into T, 16. How do we know it's a maximum? Well, earlier you remember that we had a cut which was equal to 16. There it is. That's the minimum cut. And therefore we found a cut which is equal to the flow. And so we can say that we must have the maximum flow by the max flow min-cut theorem. Well, the flow augmenting paths that we've used there were quite straightforward to find. Sometimes, however, they can be a little bit trickier. Let's consider this pattern which has been produced for the network shown. This is a flow which has come from using flow augmenting paths, and we've reached a stage where I've shown some of the saturated arcs. Now it might appear that we can't go any further, because if we try going from S, well, we can't go to C because that one is saturated, and if we just go from S to A, then we can't get to B because that's saturated. We could come down to D, but then that's saturated. You think, okay, that appears to be it. So a total flow of 36, 18 and 18. Remember that the backward facing arrows show the flow. However, there is a flow augmenting path, and it goes from S to A to D to C to B to T. The crucial one is this part here, where we're going to change the numbers against the actual direction of flow. So we're going to reduce the flow in this part of the network. The crucial thing to look for is the arrows which are facing towards T along that path are all positive. 7, 6, 15, 2 and 3. The smallest of those is 2, so we can make a change by 2 using the path S, A, D, C, B, T. So there it is marked on. Now this is what's called a backflow, because here we're going to make the change against the direction CD. Let's do that change and see what we get. Remember that the arrows which are facing forwards are going to reduce, so that's going to become 5, and this go up to 15. This one here becomes 4 and 5. This one here is going to come down to 13, that one go up to 2. This one come down to 0, and that one up to 10. And this one down to 1, and that one up to 20. So you can now see that our flow has increased from 36 that we had to 38. 20 and 18 is 38, 15 and 23. 38 coming out of S, 38 going into T. So what's happened at this CD area? Well, where it used to be a flow of 15 along CD, so that the 23 split into 15 and 8, it's still got 23 coming into C, but now it's splitting as 13 and 10. So we've just changed the flow through C. No different number, no 23 is still the same, but only 13 now going to D. So that means that the extra 2 that we've sent from S to A to D can go along this route, so that instead of that 18 there being made up of 15 plus 3, it's now made up of 13 plus 5. So we've redistributed the flow in this area of the network. And that's allowed those extra 2 to come through to here to give us a total flow of 38. The extra 2 is actually flowing from S to A to D. Well, from S to A to D. And then we've also got 2 that flows from C to B to T. How do we check that that's a maximum? We quote the max flow Mincut theorem. So you'd look for a cut of size 38. Well, that ends this particular video at looking at flow augmenting paths. In the next video we'll be looking at network flows with upper and lower capacities.